Hello, and welcome to Tech to Tech presented by KYZEN, where we will explore common cleaning questions and answers. This session has been pre-recorded and will include additional FAQs related to this specific topic at the end of the presentation. We hope it is 15 minutes well spent. Let's get started. I would like to introduce KYZEN's own Zach Papiez.
Good afternoon, William, and thank you to everyone tuning into this presentation. This presentation is on gathering objective evidence for your cleaning process and why SIR is the right tool to accomplish this. In choosing an objective testing method to characterize a cleaning process, it is important that the method is site-specific and directly concerns itself with the biggest culprit for board failures, the active residues. Being site-specific is very important because failures do not happen all across the board, but rather under specific, hard-to-clean components, such as QFNs or other bottom-terminating components. Directly correlating with board process residues is also of utmost importance because these residues are the main drivers of failures where a cleaning process is concerned. Surface insulation resistance satisfies both these conditions, making it a great candidate for managing a cleaning process. We've established that SIR is an apt choice for characterizing your cleaning process. Let's take a deeper look into the methodology background for SIR. Starting with the basics, SIR is an electrical test method that measures the resistance of an insulation across conductors of opposite polarity, otherwise known as the anode and the cathode. This establishes an electrical field, which is fundamental in mobilizing ions and creating an environment to model board failures such as leakage currents and dendritic growths, which will be discussed later. Breaking it down into its respective parts, the surface portion of SIR is defined as the distance between the conductors of different polarity. The areas of greatest concern are those with the smallest distance between anode and cathode. This distance also provides something of an upper limit for your SIR value. The insulation portion of SIR ties directly into this idea. Components with a wider pitch have more insulation than components with a tighter pitch. So components with a tighter pitch, all else being equal, will have a lower SIR value. After considering many other parts that factor into the base insulation, such as solder mask or conformal coating, the remaining flux residue must be considered. Leaving even a small amount of active flux residue from your cleaning process will greatly reduce the insulation and greatly increase your risk for failures. Finally, the resistance portion. Resistance is defined as opposition to current in the circuit. Therefore, low SIR values can indicate a failure as it would demonstrate that current is increasing across the surface of a board, perhaps forming a full-on dendritic short. Looking at the method as a whole, SIR is commonly understood as a stress test method. It is typically ran at bias conditions for 168 hours in an attempt to model the lifetime or roughly 10 years of a PCB in the field. This is accomplished by subjecting the board to temperature, humidity, and electrical bias. If you combine this with the active ionic contamination, you are likely to detect some form of board failure. Types of components on the board and their specific characteristics are also often overlooked. This is further evidence that your process must be tailored directly to your unique situation. PCBs in the field will often be subjected to a number of different environmental conditions that affect the reliability of the assembly. They must be able to withstand ambient conditions or normal day-night variations consistently. This starts with managing the hygroscopic residues common to current processes. Residues left from soldering and handling can easily mobilize given an electrical potential difference in harsh climatic conditions. This problem is only becoming more pronounced as the density of component packing is increasing with the miniaturization of these components. Detecting comparative cleanliness of a board is the bread and butter of SIR. Understanding how clean is not as easy to determine, however. Many SIR tests in different conditions are likely required to understand an upper limit for board cleanliness for your process. Likely more testing is then required to be run at an acceptable condition to verify the consistency of said cleaning process. Having said this would be impossible to accomplish without SIR's ability to detect the active residues left over from an inadequate cleaning process. Next, let's run through a few of the potential failure mechanisms that SIR can reveal that active residue facilitates. Leakage currents are how we describe what appears to be residue activity in an SIR test without exhibiting the full behavior of a dendritic short. As you can see in the right picture, there is some metal oxide migration that does not completely bridge the two fins together. This would likely appear as an unstable SIR value, potentially dropping below the 8 log ohm range into what we consider the danger zone. These kinds of failures are extremely undesirable, as they can be intermittent and hard to pin down in the field. A shorted channel occurs when the dendrite completely bridges the anode and cathode together. This is depicted on the right picture as a lightning-like structure growing from top to bottom. The accompanying SIR chart identifies this failure by depicting values remaining at the lowest resistance value the system allows for a long period of time. This chart values eventually recover from the danger zone, and the assumption is that the electrical bias eventually broke the dendrite. Finally, even mild residue effect can be seen through SIR when your boards haven't been cleaned or cleaned well enough. Some of these effects might not be technically classified as a failure by IPC standards, but setting up a cleaning process that foregoes the residue effects altogether may be desirable. Next, let's take a look at a case study that exemplifies how SIR can detect cleanliness. In this particular study, there were multiple boards soldered with a no clean flux, some cleaned and some not cleaned. These boards were prepared over several weeks and tested at the same pace. A clear discrepancy can be seen between those boards that were cleaned and those that were not. A high level of consistency can also be seen in the boards that were cleaned. This SIR depiction is the best case scenario for a cleaning process. The consistency would indicate not only repeatability of the process, but also a high degree of cleanliness. A process that could leave residue on a board would not show this tight of a data set. The fact that a no-clean solder paste was used must also be duly noted. The residues left over from a no-clean process are usually much less active, but SIR was still able to detect a clear difference between the not and clean conditions. Even with a no-clean solder paste, a clean board is still better than not. Now let's take a look at a few frequently asked questions on the topic. Firstly, what is considered a failing SIR value? Technically, below 8 log ohms is considered failing, but the meaning behind the resistance value is largely process and board specific and should not be taken as gospel. Secondly, why is SIR tested at 5 volts as opposed to a much larger voltage? There are actually two major reasons why SIR is commonly tested at 5 volts. First, the 5 volts closely mirrors the operating voltage of most electronics today, but also the lower voltage greatly increases the chance that the testing will catch a dendritic failure. A higher voltage would break the dendrite much faster and it might not be detected. Lastly, why is the site-specific nature of SIR so important? The reason for this is that board failures occur on a site-specific basis and not usually due to problems averaged across a board. This is especially important for cleaning processes where you must clean towards the most difficult components. Thank you. This concludes my presentation. I will hand it back to you, William.
Thanks, Zach. And thank you all for watching this Tech to Tech session. If you would like to discuss this topic further or have any questions not answered in the session, please contact your local Kaizen regional manager or send an email to tech@kaizen.com, and we will have someone follow up with you as soon as possible. Do you want to have exclusive access to future content sent directly to your inbox, or do you know someone who would benefit from these sessions? If the answer is yes, just go to tech2tech.kaizen.com and fill out the subscription form. And if you like this video, be sure to follow us on our social media platform for more expert cleaning content.